I would like to introduce the second experiment of the Physical Chemistry Laboratory 2, which is entitled, as you can see here, vapor pressure of a pure liquid. Content, purpose, the theory, apparatus and reagent, procedure, result, quotients, references. So let me start with purpose of the experiment. So in this experiment, we would like to gain understanding about the liquid vapor equilibrium and determine the heat of vaporization, which is generally represented as delta H VAP, by measuring changes in vapor pressure as a function of temperature. Theory. Let me start with phase. What is phase? Phase is a physically distinctive form of a substance such as the solid, liquid, and gaseous state of ordinary matter. Okay, so solid, liquid, gas, typical three different phases of a substance. Phase transition, the transformation of a thermodynamic system from one phase to another. Ice melt to liquid water, melting. A typical example of phase transition. So water liquid vaporizes to water vapor. Another example of phase transition. Phase equilibrium. Phase equilibrium. This is the situation that more than two phases coexist with keeping equilibrium. At equilibrium, the chemical potential of different phases of a substance is constant throughout a sample, no matter how many phases are present. You can see here phase diagrams of water and carbon dioxide. In a phase diagram, on the y-axis, you have pressure, right? On the x-axis, you have temperature. The same also here, pressure and temperature. A phase diagram is basically a summary of which phase shows the lowest chemical potential, or which phase is the most stable phase for a given pressure and temperature. This is then considered for a range of pressure and a range of temperature, and summarized with a two-dimensional plot, which is called then phase diagram. In this area of pressure and temperature condition, solid phase of H2O, so this is a phase diagram of H2O, so solid phase shows the lowest chemical potential, the most stable, well, chemically the most stable, so probably better to say having the lowest chemical potential. So here liquid shows the lowest chemical potential. And one can say that thermodynamically, liquid is the most stable phase here in this area of the temperature and pressure. So here, gas phase shows the lowest chemical potential among three different phases, solid, liquid, and gas. So let's consider what happens when the pressure is fixed at 1 atm and you have H2O, and originally you have a temperature of minus 20 Celsius degree, and you supply heat to warm up the system, okay? The pressure fixed at 1 atm, okay, you start somewhere here, far below 0 Celsius degree, and then you supply heat to the H2O. Of course, at the very beginning, at this temperature, which is quite cold, far below 0 Celsius degree, you have ice. When you supply heat, then temperature increases. At this point, ice melt, so solid converted into liquid or water. When this phase transition is completed, then the temperature can be further increased, and then of course, I mean, this is 0 Celsius degree, right? So the temperature that ice melt under 1 atm, that is the melting point of water. Well, we know that that is 0 Celsius degree. So after this phase transition, temperature further increases, okay? And then when the temperature reaches 100 Celsius degree, then the second phase transition takes place, which is the phase transition from liquid to gas, right? Okay. So this is boiling point, right? When the phase transition is then completed again, then the temperature can be increased further. So here, solid shows the lowest chemical potential. Here, the liquid phase shows the lowest chemical potential. Here, the gas phase shows the lowest chemical potential. And on that point, solid and liquid, they show the same chemical potential. At this point, liquid and gas, they show the same chemical potential, right? So here you have an equilibrium on the 1 atm. Here, at this temperature, 0 Celsius degree, you have an equilibrium of the chemical potential for solid and liquid. Here again, the equilibrium between liquid and gas, right? Any point actually on this boundary, any pressure temperature point on this boundary, under these conditions, you have the equilibrium between solid and liquid, okay? So on any point on this boundary, you have the equilibrium between solid and liquid. The equilibrium between liquid and gas. So the chemical potential between liquid and gas are the same here. When you have a pressure below 0.006 atm, which is very small pressure, then at very low temperature, you have ice, solid phase of H2O. And then when you warm it up, you directly go to the gas phase without passing through the liquid phase, okay? So you first have solid and it goes directly to the gas phase. This is called sublimation, another example of phase transition, okay? So then you have this boundary. On this boundary, you have the equilibrium between solid and gas. That means that you have the same chemical potential for solid and gas, right? The same here, solid, liquid, gas, boundary between solid and liquid, boundary between liquid and gas, boundary between solid and gas, okay? You may have learned about why this slope is negative while this slope is positive for CO2 in general chemistry. So today I don't want to go into that issue. Now, you have this point, which is called triple point. On that triple point, three different phases of a substance, solid, liquid phase, they all have the same chemical potential, okay? So all the three phases are in equilibrium on that triple point. Okay, so next topic, vapor pressure. The pressure when a pure liquid is placed in an evacuated bulb and the liquid and the gas reach at dynamic equilibrium at constant pressure, the pressure at this dynamic equilibrium exerted by the gas phase molecules is the vapor pressure at that constant temperature. Think about an evacuated bulb, so completely sealed system, okay, a closed system. Inside the closed system, you have liquid, okay? You have liquid and you have vacuum. So vacuum basically means nothing. So no gas molecules, okay? Now, under this circumstance, what is happening is that the surface molecules of the liquid escape from the liquid phase and go to the gas phase. So vaporization takes place. So basically, when you have liquid, then the surface molecules of liquid can vaporize. Basically, the rate of evaporation, how many molecules are actually converted into the gas phase molecules for a given time, that is actually proportional to the number of surface molecules of the liquid. So simply speaking, surface area of the liquid. And that is basically the same as a function of time. When some liquid molecules from the surface are evaporated, then you have still the same surface area of the liquid, right? Because the next liquid molecule will be exposed, and then the surface remain the same in area. So number of surface molecules remain the same. So basically, as a function of time, rate of evaporation is the same, right? Now, at the beginning, there is nothing in the gas phase, so no gas molecules can go back to the liquid phase. But as a function of time, as the gas molecules increases in number, as you have more and more gas phase molecules, the condensation rate increases. The condensation process means that the gas molecules goes back to the liquid phase, okay? And that is the rate of this process, condensation, is proportional to the number of gas molecules. As the number of gas molecules increases, then condensation rate also increases, right? So at a certain point, the rate of evaporation, rate of condensation, they remain the same. They become the same. And then number of gas molecules doesn't change anymore as a function of time. Of course, some of the gas molecules condensate to the liquid phase. Some of the liquid molecules evaporate, but the rates are the same. So number of gas molecules, number of liquid molecules remain the same, and that is dynamic equilibrium, right? And then when this dynamic equilibrium is established at a constant temperature, the pressure exerted by these gas phase molecules, that is vapor pressure. So ideally speaking, when you consider these gas phase molecules ideal, then we can apply ideal gas equation PV equals nRT, PV equals nRT, okay, for a given temperature, for a given number of moles of the gas phase molecules, for a given volume, then you should have some pressure exerted by these gas phase molecules. And this pressure, that is the vapor pressure of that liquid for a given temperature, for that constant temperature. Okay? So this vapor pressure depends on the intermolecular force and temperature. When temperature increases, then vapor pressure increases. The intermolecular force is also very important here. When the molecules in the liquid, they show stronger intermolecular forces, then they do not tend to vaporize more. They tend to stay more in the liquid form, okay? Then the vapor pressure becomes lower. When the intermolecular force is lower, then they can easily vaporize, so the vapor pressure becomes larger. At a higher temperature, the vapor pressure becomes higher. And as the intermolecular force becomes lower, the vapor pressure becomes higher. So vapor pressure, temperature, this is the vapor pressure curve for diethyl ether, ethanol, ethyl alcohol, water, ethylene glycol. Okay, for all liquids here shown in this graph, the vapor pressure increases as a function of temperature. And well, diethyl ether showing the lowest intermolecular force shows the highest vapor pressure. Ethanol next, and water showed substantially high intermolecular force, okay, due to the hydrogen bonding. It shows a lower vapor pressure. Ethylene glycol shows the lowest vapor pressure with the highest intermolecular force among these four substances. Okay, Now we go to boiling point and vapor pressure. The boiling point of substance is the boiling point of a substance is the temperature at which the vapor pressure of the liquid equals the pressure surrounding the liquid. It depends on the surrounding pressure, right? So we know that on the 1 atm, when you have water, on the 1 atm of the pressure, when temperature becomes 100 Celsius degree, then it boils, right? So this is boiling point. Boiling can be found, right? Boiling, right? So water boils at 100 Celsius degree. When you look at the vapor pressure of water here in this plot, okay, then you can see that at 760 torr, corresponding to 1 atm, of the vapor pressure, that vapor pressure can be reached for water at 100 Celsius degrees. So this is 100 Celsius degree, and this is the vapor pressure plot of water. For water, when water becomes 100 Celsius degree, then the vapor pressure becomes 1 atm. So when the external pressure is 1 atm at 100 Celsius degree, because the vapor pressure is 1 atm, the external pressure and vapor pressure become the same, and that is the boiling. When that happens, the temperature where that happens is the boiling point. Okay, at that temperature we see boiling of water. The external pressure, vapor pressure, the same, and that is the boiling point. So when liquid boils, then one can say, okay, at that temperature, external pressure and internal pressure, the vapor pressure should be the same. And of course, you know that when you go to lower pressure along this curve, then when the vapor pressure becomes lower, then temperature on this curve becomes also lower. Okay, so that means that when the external pressure is lower than 1 atm, then water boils actually at a temperature below 100 Celsius degree. Right? So for example, let's say when external temperature is 600 torr, let's say this is roughly 95 Celsius degree probably. Okay, so when you have water, when the external pressure is not 760 torr, but only 600 torr, then this boiling will take place roughly 90 to 95 Celsius degree, right? 90 to 95 Celsius degree, because at this temperature, vapor pressure is 600 torr, okay? And boiling, when external pressure is lower, then that respective vapor pressure can be reached at lower temperature, so the boiling temperature becomes lower. Okay, molar heat of vaporization. Heat of vaporization, the energy that is needed to make gas out of 1 gram of molecules in liquid at the same temperature, molar heat of evaporation, generally, as I already mentioned at the beginning of my lecture today, represented by a symbol delta H VAP. Well, the typical unit is joule per mole or kilojoule per mole. Molar heat of evaporation. So this is the energy that is needed to make gas out of 1 mole of molecules in liquid at the same temperature. So how much heat is needed for the phase transition from liquid to gas for 1 mole of a substance. That is the molar heat of evaporation or molar heat of vaporization for a substance or for a specific molecule. So I mentioned at the very beginning, chemical potential is very important concept here in phase diagram. Okay, so let me first start with Gibbs free energy, and then later I'm going to explain about the chemical potential. Chemical potential is directly related to the Gibbs free energy. If you want to understand chemical potential, you first need to understand Gibbs free energy. Okay, by definition, Gibbs free energy, G, equals H enthalpy minus Ts, T temperature, S entropy, right? When you think about infinitesimal change of the GHTS, then dG becomes dH minus SDT minus TdS. Okay. And we learn in general chemistry that enthalpy is U plus PV. U, internal energy. We already learned about internal energy in the first experiment, in the theory of the first experiment, right? So internal energy. So H is U plus PV. P pressure, V volume. Okay. So here again, dH becomes then du plus PdV plus VdP. So, and then we also learned in the first experiment that delta U is Q plus W. So du is dQ plus dW. And you're going to learn about this probably. I just want to just mention that that dq is t ds actually in the reversible process, right? So probably I don't want to go into too much details about this issue. So probably you are going to learn about this in physical chemistry 2 class. So dq is basically tds in the reversible process. Okay. So I just want to mention that, I mean, this is something related to Clausius equation, Clausius inequality. So when you consider reversible process, then dq becomes tds and dw becomes then p dv. Okay. So, and then when you combine all this together, okay, so when you insert 3 and 4 to the equation 2, so this is 2, 3, 4. So when you insert this, so du, dh to so you first need to you have dh du here, okay. So du should, this should go to here, right? And then this dh goes to here, okay. And then you end up with this, okay. TDS, let's see. So dg, well, okay, this when you combine dh is t, when you combine, well, 3 and 4, when you combine 3 and 4, tds minus p dv, that is du, plus p dv plus v dp. So basically then dh becomes tds plus v dp because they are removed, okay, dh, okay. And then now dg, okay, let me, I already removed that. So tds vdp minus sdt, okay, minus tds, okay. And then they are removed as well. And then vdp minus sdt, okay. So dg becomes then vdp minus sdt, okay. I just want to mention once again that this relationship is based on the reversible process, and this is somehow related to this Clausius inequality. I think I don't want to go into too much details about this. You're going to learn about this in physical chemistry too. Okay. Okay. So important conclusion, anyhow. VDP minus SDT, right? I think this is something worth remembering. E.g., VDP minus SDT. Okay. So Gibbs-free energy. Using Gibbs-free energy, we can decide whether the reaction is spontaneous or not under constant pressure conditions. So spontaneous reaction delta G is negative. We learned about that already also in general chemistry. I think general chemistry too, right? So it is also the chemical potential that is minimized when a system reaches equilibrium at constant pressure and temperature. So we already learned that chemical potential is very important for the phase issue, right? Uh, Now we are going to the chemical potential. So the chemical potential in thermodynamics, chemical potential mu, also known as partial molar free energy, is a form of potential energy that can be absorbed or released during a chemical reaction for one component system. When you have only one component system, then one can say mu is simply molar Gibbs free energy. So the chemical potential can be given as the first order partial derivative of Gibbs free energy with respect to number of moles, okay, considering that pressure, temperature, and the number of moles of other component remain the same. So basically, when you have only one component, then one can say this is simply the Gibbs free energy for one mole. That is chemical potential, right? So molar chemical potential. This is chemical potential for one component system. And also, I mean, in our experiment, we also deal with one component system. We have pure liquid, one component. For a pure liquid, one component, pure liquid of one component, we are going to then we are going to measure the temperature and vapor pressure. And based on that, we would like to determine the delta HVAP value, the molar heat of vaporization evaporation value for that given one component substance. So we are going to do that for multiple different substances, but for each experiment, we have one component system. So in this case, chemical potential can be regarded as just Gibbs free energy for one mole of that substance. It may also change during a phase transition. So the chemical potential can change. During the phase transition, the chemical potential of a species in a mixture can be defined as the slope of the free energy of the system with respect to the change in number of moles of just that species. Okay. Okay, I don't want to go into that much details about this mixture issue. So this is what equation is showing you. So I think probably today we would like to more focus on the one component system. Okay. Important thing, under equilibrium, as I already mentioned, when two different phases are in equilibrium, then chemical potentials of these two phases should be the same. If there would be alpha phase and beta phase, I mean, they could be either solid, liquid, or gas. If two phases would be in equilibrium, their chemical potential should be the same, right? Okay. So we learned that dG equals VdP minus SdT, right? That is something we learned actually from here, right? From here. So when you consider the pressure is remaining the same, then you can remove that, right? Because dP, that means that dP becomes 0, then dG becomes then minus SdT. So then for a pure substance, which is one component system, you can just think that chemical potential is simply molar gives free energy, right? So then simply one can say that du would be minus Sm dt, right? So du would be then dg, du would be d mu, I'm sorry, d mu would be dgm, okay? So this is actually indicating that the first order derivative of the chemical potential with respect to the temperature, that should become the molar entropy, right? Minus negative molar entropy. That means that when you have temperature on the x-axis, and then on the y-axis you have chemical potential, the slope, and then you have the chemical potential changing as a function of temperature, okay? So this plot is basically showing how a substance's chemical potential changes as a function of temperature. In this plot, the negative value of the slope becomes then molar entropy, right? So regarding the molar entropy, we know that gas shows the highest entropy, the next highest entropy, liquid, okay, and then solid shows the lowest entropy, right? So you can see for the gas phase, this curve is really steep. So minus S value, minus slope is actually very large. And that is because gas shows very high entropy. The negative slope is entropy. When the curve is very steep, that means that entropy of that phase is actually very large, right? So this curve is how the chemical potential of gas phase changes as a function of temperature, okay? And then this is very steep because gas phase shows the highest entropy. Next one, this curve shows how the chemical potential of liquid changes as a function of temperature. Now, the curve is not that steep anymore. For solid phase, how the chemical potential changes as a function of temperature. So, I mean, the slope is actually almost nothing here. So, considering that the negative value of this slope correspond to the entropy, and that the entropy of gas is the highest and liquid next highest and solid, that of solid the lowest, then you understand that this curve corresponds to the chemical potential change of the gas phase as a function of temperature, that of liquid, okay, that of solid, okay. And then you can see here, solid shows the lowest chemical potential, so you have solid phase. Solid phase is the most stable phase because in this temperature area, solid shows the lowest chemical potential. In this temperature area, liquid shows the lowest chemical potential. In this temperature area, the gas phase shows the lowest chemical potential, okay? So this curve goes like this. This curve goes like this. This curve goes like this, okay? So this is the lowest here, this is the lowest here, and then this is the lowest here. So solid is the lowest in chemical potential here, liquid is the lowest in chemical potential here, then gas phase is the lowest in chemical potential here. So that's why here you have solid phase, liquid phase, and gas phase. At this point, solid and liquid have the same chemical potential, okay? That is actually the boundary, corresponding to the boundary at the phase diagram, where phase transition takes place. Again, this point corresponds to the temperature where you have the same chemical potential between gas and liquid, okay? Again, phase transition takes place. Here, of course, I mean, in this plot, pressure is considered to be the same, okay? Of course, in phase diagram, we have also seen the phase changes phase behaviors at various pressure ranges. And in this plot, you have only one single pressure. The pressure is constant, and you consider how the chemical potential of each phase changes as a function of temperature. Okay, so the slope, pure substance, mu gm. I already explained it. The slope of graph is entropy. Above the boiling point, the value of Gibbs free energy of liquid, or better to say, the molar chemical potential of liquid is larger than that of the gas. So gas is the most stable above the boiling point. Okay. Compressibility factor. Okay, so we know PV equals nRT. Well, in this ideal gas equation, in principle, nRT PV should become 1, but in reality, we know that that value is not necessarily 1, right? So ratio of the molar volume of a gas to the molar volume of an ideal gas at the same temperature and pressure, that is called compressibility factor, which is given as C, okay? Useful thermodynamic property for modifying the ideal gas law to account for the real gas behavior. So you can see here that as a function of pressure, in principle, according to the ideal gas equation, the value should be 1 over the entire pressure range, but I mean that value actually changes quite a lot as a function of pressure, right? So this is basically deviation from the ideal gas behavior, right? Now you have here PR and PR, which is given as T over Tc, P over Pc. Here, Tc is the critical temperature, and Pc is the critical pressure. And that is for each substance, you have a given Tc value and Pc value. Principle of corresponding stage. All fluid, when compared at the same reduced temperature, Tr, and reduced pressure, Pr, have approximately the same compressibility factor and all deviate from ideal gas behavior to the same degree. Okay, the reduced form of Van der Waals equation applies to all fluid. So for every substance, this critical temperature and critical pressure, Tc and Pc, this critical temperature and critical pressure for every substance is different, okay? And even if the Tc and Pc values for different substances are different, when you compare the Z value at a given Tr and Pr value for many substances, the Z values are quite similar. That is the principle of corresponding state. Of course, for a given T and P, this is a real temperature, and this is the real pressure, okay? For given T and P, of course, different substances should show different compressibility factors, okay? But when you consider the compressibility factors of a given Tr value, okay, and Pr value, so when you have two different substances, same Tr and Pr for two different substances does not mean that you consider the same temperature and pressure for two different substances, because they have different critical temperatures and critical pressures, Tc and Pc values, okay? So you have to consider different temperatures and pressures for two different substances so that the Tr and Pr become the same, and then under these conditions, the compressibility factor become quite similar, approximately the same, compressibility factor. So that is the principle of corresponding state. Okay, now we are going to Clausius Clapeyron equation. We learn about this also in general chemistry 1 actually, but in general chemistry 1 we learn about only the final equation. So I'm going to show you today how this final equation we learn in general chemistry, which is known as Clausius Clapeyron equation, can be derived. The Clausius-Clapeyron relation or equation is a way of characterizing this continuous phase transition between two phases of matter of a single constituent, a single component, on a pressure-temperature diagram. So pressure-temperature diagram. So this is basically the phase diagram, but we only see actually a part of the phase diagram where you have two different phases and you have boundary between two different phases. So, for example, you have phase alpha. Well, alpha, let's say liquid, okay, and beta, let's say gas, okay. So, and then you have the boundary, okay. This is boundary corresponding to the equilibria between liquid phase and gas phase, alpha and beta, right? So on a pressure temperature diagram, the line separating the two phases is known as the coexistence curve. This is the coexistence curve, okay? This is coexistence curve. The Clausius-Clapeyron relation gives the slope of the tangent to this curve, okay? So let's see the derivation process for the Clausius-Clapeyron equation more in detail. So as I already mentioned, well, this is things that I already explained. I already explained that this as well. So chemical potential is for one component system, molar Gibbs free energy, and dG equals VdP minus SdT. Okay, I explained about them all. Okay, so these are basically things I already explained. Okay. So I think, I mean, I showed already this, so I don't have to repeat. Okay. Now, in equilibrium, liquid vapor equilibrium, I already mentioned that the chemical potential of liquid and chemical potential of vapor should be the same. And along the coexistence curve, so as long as the equilibrium is maintained, when there would be infinitesimal change of the chemical potential of liquid, the same amount of change of the chemical potential should be also considered for the gas phase. Because in equilibrium, so basically, I mean, liquid phase and gas phase at a given point of the okay, so you have this coexistence curve, right? At a given point, you have the same chemical potential of liquid and solid, liquid and gas, alpha and beta. When you go to another point, so that the chemical potential of alpha or chemical potential of liquid is changed, the same amount of change of the chemical potential should be also valid for the gas phase, because you are still on the equilibrium. You are on the coexistence curve, right? So one can say that the chemical potential of L is the same as the chemical potential of G, right? And then, well, you go ahead, you can use actually this this relationship here, because that of liquid and that of gas is the same. Vm liquid dp minus entropy m liquid dt should become, so this is this, and this is basically this, considering this, they should be the same, okay? And then rearranging, it becomes like this. So, and then this is delta V. Delta V, basically the volume difference between gas and liquid, the entropy difference of gas and liquid, okay? So delta S is then basically how much of the entropy is changed for vaporization, and how much volume is changed for vaporization. Okay, this is basically what delta S and delta V means. Okay, and then, well, this becomes then like this, and then considering this, then it can be written as this, and of course delta S VAP is delta H VAP over T. Okay. This is again related to the Clausius inequality problem, and I don't want to go into too much details again about this, the relationship between heat, temperature, and entropy. So probably this is an issue that you're going to learn more in detail in physical chemistry too, probably. Okay, so when you apply this relationship, then it becomes like this. Okay, and then what you can do is the following thing. For delta V, okay, that is roughly speaking the VMG, right? And that is because delta V is basically volume difference between gas and liquid. Comparing to liquid, volume of gas is much, much larger. So this volume difference between gas and liquid can be regarded as basically the same as volume of gas. So because volume of gas is much, much larger than volume of liquid, okay? Then when you apply ideal gas equation, okay, and then volume of gas is approximately then for 1 mole volume of gas, according to the ideal gas equation, becomes then RT or P, okay, and therefore delta VAP can be then simply written as RT or P, okay. So when you then apply this to this point, okay, and then we write the things all together, and then you come up to this equation, okay, and then you then rearrange the equation, and then it becomes like this, okay. So I think, yeah, I think there is not that many important things that many difficult things that you cannot understand, right? It looks actually complicated and long, but when you look at step by step, it's not that much complicated. Okay, so you basically come up to the conclusion that dP over dt, the first order derivative of pressure with respect to temperature, okay, that is given like this. Okay, so, and then ultimately you have this equation, right? You have this equation, and then you make integral. Okay, integrate the equation, and then it becomes like this, okay. So integrate the equation from P1 to P2, P1, P2, and then T1 to T2, okay, and then it becomes like this. So, and then you can also just simply P dP. So this is actually one path. Then you can come up to this rather simple equation. But on the other hand, what you can do is that dP over P, okay, and then delta H VAP and RT square dt, okay, and then this can be rewritten like this, okay, and then there are some rearrangement you have to then consider, right? So it can be then rewritten like this, okay. This is given then like this, if we're starting from here, okay, and then this is basically the same as this. I mean, this can be converted into this according to the ideal gas equation, okay. Now, the point is, if the thing would be ideal, okay, then you can actually consider your equation to be like this. But when you introduce the compressibility factor, okay, for the real gas, then you can actually come up to this equation, okay. And then ultimately you can come up this equation. So starting from the end of last slide, starting from this, you make an integral and come up to this equation, or probably you go ahead here further and then rearrange using this equation, these relationships, and then consider the real gas. Consider the real gas compressibility factor, okay, and then ultimately you come up to this equation, right? And then, so basically, this and this, they basically mean the same thing, right? Okay. So when you have logarithm pressure on the y-axis, okay, and then 1 over t on the x-axis, okay, and then the slope will be minus delta H VAP over NR. So you'd like to actually get this molar heat of vaporization, right? And this is basically meaning the same thing. Of course, I mean, here you don't actually take the compressibility factor into account for the real gas, but without compressibility factor, then you can basically say that for 1 mole, okay, so this is actually for n moles, the equation is actually holds is valid for n mole, okay. For when you actually just simply consider 1 mole system, that this can be just 1, okay. And then here, when you just think about a situation that your gas is ideal gas, then this is also 1. Then basically this and this become the same, okay? So anyhow, I think the final equation we are going to use is actually this one. But you'd like to make the thing a little bit less complicated. This should be delta H VAP, right? So relationship between delta H VAP, molar heat of vaporization, and temperature variation. So according to something called Kirchhoff law, delta H VAP at a temperature of T2 equals delta H VAP at a temperature of T1 plus delta Cp, this is the constant pressure heat capacity. We already learned about that in the first experiment. T2 minus T1, okay. And now in general, delta H VAP and Z, the compressibility factor, and delta H VAP both decrease in temperature, and therefore we can consider this as a kind of constant, okay? Because this also changes as a function of temperature, but that also changes as a function of temperature. So that can be regarded as a constant, and R is of course constant. So at the end, actually, we come up to the same conclusion as general chemistry. So in general chemistry, we learned about this equation. So here we didn't consider any compressibility factor. This equation is actually just simply from an assumption that we have 1 mole of the substance, and the real compressibility factor was not actually considered here. Only ideal gas equation was considered. We come up to this equation, okay. And now, in this procedure, second procedure, we considered the real gas compressibility factor. So the real gas non-ideal behavior, and then we came up to this rather more complicated equation, including the Z compressibility factor. But anyhow, this again here can be regarded as a constant, because this decreases as a function of temperature, this decreases as a function of temperature, so we can just consider this as a constant, okay? So in general chemistry, we just considered this as a constant without considering any compressibility factor. As a matter of fact, delta HVAP is not a constant that can change as a function of time, but Z compressibility factor that also changes as a function of time. As a function of temperature, delta HVAP changes as a function of temperature, but Z also changes as a function of temperature. So ultimately, delta HVAP over Z can be regarded as a constant, coming up to almost the same conclusion to the equation we learned in general chemistry. This is actually the equation that we learned in general chemistry. We come up to almost the same conclusion, basically the same conclusion, right? Okay, now we are going to the experimental part. Apparatus: 5-liter ballast bulb, electric heating mantle, thermometer, rubber cap, boiling chip, 3 rubber tube, 2 neck, Glycine flask, reflux condenser, closed tube, mercury, manometer. Manometer, we already learned about this word manometer in the first experiment. This is the apparatus which you use for the pressure measurement. Your experimental setup will look like this. You have bulb, okay? You have bulb. This is a system, okay, which just occupies some volume, right? So we need some volume here in order to be able to control the pressure appropriately. So you have mantle, you have your liquid here. Your liquid is here, okay? Your mantle, heating mantle is of course heating your liquid inside the flask. You have a flask here and you have liquid, okay? We are going to use 3 different liquid: benzene, and heptane, and distilled water. So with benzene, we are going to run an experiment, okay? And then with N-heptane, again the same experiment. With distilled water, again the same experiment, okay? So, and then ultimately, you will be able to determine the delta H VAP over Z value for benzene, for N-heptane, for distilled water. 3 different delta H VAP over Z values should be determined, okay? Let me just roughly explain you how you have to do the experiment. This is your reflux condenser, right? This is your reflux condenser. This is your thermometer. You read the temperature, right? You have your liquid, and you have your heating mantle, right? So here you have either benzene and heptane or distilled water, okay? And then here you have tube, ballast bulb, okay? And then you have a pump. So, and then you have stopcock here. So you have pump here. So somewhere you will have pump, right? To evacuate the whole system. And then you have the closed tube mercury manometer. So this is the manometer with which you can use the pressure. So basically, what you are going to do is that you are going to determine boiling point at a given pressure, external pressure. Okay, so you are going to then measure change of the external pressure, and as a function of the change of the external pressure, how the boiling point changes will be measured for each liquid. So 3 different liquids. For each liquid, you change the external pressure, and then you change how the boiling point changes. Then, of course, in here, the system is considered to be always in equilibrium. So external pressure we measure with this manometer, mercury manometer, can be regarded as the vapor pressure. Okay, so we get the data for the boiling point with various vapor pressures. So basically temperature and vapor pressures. Okay, so because at boiling point, external pressure can be regarded as the same as vapor pressure, right? So when you measure external pressure, then vapor pressure can be measured, okay? So, and then that vapor pressure at that temperature. So basically, we measure boiling point, external pressure. You change, so external pressure, 1, 2, 3, 4, 5. So, and then when you change external pressure, how the boiling point changes will be measured, okay? And then this external pressure is basically corresponding to the vapor pressure, and this is basically the temperature, and this T and P, this goes to the Clausius Clapeyron equation that we already learned here, okay? Goes to this equation, and then we can get actually this value, okay? So external pressure we measure goes to this P, the boiling point we measure goes to T, okay? Okay, procedure. The vapor pressures of benzene and heptane water in this experiment will be acquired as a function of temperature. Okay, fill 1/3 of the Kleisen flask with the liquid. So either benzene, heptane, water, or water. So first you fill liquid here. Okay, this is 2 Kleisen flask, so you fill liquid here first, and then warm up the heating element. So you have flask, 1/3 of the flask is filled with liquid, and then warm up the heating element. And then you measure the boiling point when the liquid is boiling and remove the heating element, right? So when you see the liquid is boiling, then remove your heating element, okay? Read the pressure and temperature simultaneously as soon as the value becomes stable. So the pressure reading requires the value of atmospheric pressure to give the vapor pressure. Thus, record the atmospheric pressure in the laboratory. And then follow the table below to change pressure, measure the boiling point, boiling temperature for each pressure. So first, the pressure is at 700 torr, okay? Then you measure the boiling point, okay? And then I showed you that there is a tube which goes to the vacuum pump, right? So you then run the pump, decrease the pressure, okay, and then do the experiment again, and then start to see to warm up the liquid and see the boiling of the liquid, okay, and then you measure temperature, okay, and then you pump up the system further, decreasing the pressure, okay, and then measure the boiling point again. You do that actually for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 10 different pressures. So for each pressure, so you pump up the system for each, and then you measure the pressure, and that given pressure, then you measure the boiling point, okay? And then you do that also, you pump up all the system way down to 90 torr, and then you do that with ascending pressure. So that is actually what is given in the manual. But as a matter of fact, you are going to do the experiment a little bit differently. So I think your teaching assistant will be able to help you quite a lot actually here in this experiment. First, you have to make your experimental setup like this, okay? And you all connect the instrument and tubes like this, okay? And then your pump should be connected here. And then you open it and you have to pump out your system, okay? And then what is very important is that you are going to have all these connections. They should be substantially vacuum tight, okay? So that you should be able to go down to below like 90, I think 90 millitorr, right? Or 90 millitorr, right? So if these connections are not really tight, vacuum tight, but if you have many leaks there, then you're not going to get actually that low pressure. So in order to get to something like 90 or 80, even go to 70 millitorr, quite low pressure, by evacuating the whole system with the vacuum pump, the whole system should be quite tight so that you don't have actually that much leaks there, okay? And then when your system is actually evacuated to some extent so that the pressure becomes lower than something like 90, 80 millitorr, okay? And then you close it. And then you start to heat the liquid, okay? Now, and then you will be able to see that the liquid boiling. And now what you're going to see is actually something like this. Because your system is leaking though, because even if you actually do your best so that you can evacuate actually the system very well, still you have some leaks in your system. So as a function of time, if you close the system after evacuating below something like 80 millitorr, you evacuate the whole system, then the pressure will gradually increase as a function of time. So your pressure will gradually increase as a function of time, okay? And your liquid will boil, and the temperature then will actually increase as well, right? So this liquid is further boiling and boiling. The system's pressure is automatically increasing due to the leak that you should have actually in your system, the temperature increases. That means that due to the system can be regarded as in equilibrium at any point, the pressure is gradually increasing due to the leaking of the system, and temperature also increases continuously, right? So after evacuating, you heat, so your liquid boils, and then during the pressure increases slowly and temperature increases slowly during boiling. You just take a movie with your cell phone, okay? And then later on from this movie, you take like 10 different points of temperature and pressure, okay? So you do that actually for all three liquid, benzene and heptane and distilled water. Make sure that it is not that easy to make the well-sealed system. So you have to make very good sealing, okay, to go down to 80 milliliter or something like that, okay. If you reach actually that relatively low pressure, then you can just stop, you can just close it, you turn off the pump, you heat your mantle so that you start to see the liquid boiling, okay, and then gradually you will see automatically, you don't have to do anything. So gradually, naturally, you will see that pressure increases and temperature increases, okay. So you just take the movie with continuous increase of the temperature and pressure, and then later on from this movie take some data point of temperature and pressure, which can be used for evaluating your data based on the Clausius-Clapeyron equation. So you don't have to do like this, okay? So in principle, what you have to do is that you evacuate more and then measure boiling point, you evacuate more, measure boiling point. You have to do that multiple times in principle, but here you don't have to do like this. And you cannot do actually this. So data evaluation, all the Celsius temperature reading to convert all the Celsius temperature reading to absolute temperature T and draw a graph plot LNP versus, so LNP versus 1 over T. So you have many P values, many T values you can take actually from your movie, and then you will have actually LNP, respective LNP values, 1 over T values, this on the y-axis, this on the x-axis, plot your data point, okay? And then you draw a straight line. We can obtain a straight line, determine the slope of the straight line, okay? Your data point will be like this, and you can get a straight line with the minimum deviation from the data point, okay? Then you can get the slope, right? The slope should be this, right? Slope should be this, minus delta H VAP divided by RZ, okay? Which should be constant. And then, of course, then you can determine this one because R is gas constant, right? And we can ask, and now, well, from this TR value, so for N-heptane, this critical temperature is given to 540 Kelvin. For water, critical temperature is 648 Kelvin. For benzene, critical temperature is 563 Kelvin. So for a given TR value, which is TR, reduced temperature, which is, as I already mentioned, T over TC, for each substance, TC is given. So for a given temperature, when Z is determined from this plot, so this plot shows how Z changes as a function of TR value for all three different liquids. So for a given temperature, the given temperature can be converted into the reduced temperature for that substance, and then Z value for that reduced temperature can be determined from this plot, and based on that, with your experimental data and evaluated a slope of your plot, based on this, then you can determine ultimately delta HVAP, right? And then you can compare your delta HVAP with the literature value for all three liquid. Okay, so cohesion, when using heating mantle, do not heat element too quickly. Do not open stopcock S and X simultaneously. I think probably you're not going to actually use in your this is stopcock X, which is actually the valve connected to the mercury manometer, and stopcock S is this one. So if you open this and this at the same time, then mercury can be then pulled like this. So it is dangerous. But I think in the real experiment, you're not going to use this kind of mercury manometer, but you are going to use some other digital manometer. So you don't have to worry about that actually. So in principle, the experiment is designed to use the mercury manometer, but I think in the reality, when you go to the lab, then you're going to use digital uh, uh, manometer for reading pressure, so you don't have to worry about this actually. So put boiling chips in the liquid to be studied. Okay. Okay, references. All right. Then next I'm going to introduce you the third experiment. Okay, so that's it for today. Thank you.